Alright, so here we are with the logarithm notes. We're calling these the Chapter 4, Section 4 notes. The reason that we need logarithms is for problems such as the one that is shown here. So what we've done in the past, if we've had an exponent, was that we've done the root of that exponent. So if we had a power of 3, we've done the third root. Power of 2, we do the square root to undo it. But we don't have like an x root. So the idea here is that we would go ahead and take the time to guess what the answer might be. So basically you're taking 10 and you're going to raise it to something. So if I take 10 and raise it to a guess of 0.5, what's going to happen is if I put in a 0.5, 10 to the 0.5, I'm going to get 3.1622. So clearly that is not 5, and we are trying to get as close to 5 as possible. So let's go ahead, and powers do change quickly, so we're just going to do 10 to the 6. So 0.6 is what I'm using as my x value, and so I get 3.9811. Okay. That's very close to 4, and it almost jumped an entire piece by just going up by 0.1. So I'm going to also go up by 0.7. So 10 to the 0.7 gives me 5.01187. So that's, of course, more than 5, and so we don't necessarily want that. We want to go back down a little bit. So how do we go back down between 6 and 7? Well, we could go ahead and put 0.66 or something very in the middle or in between. So I'm going to do 10 to the 0.66, and I'm going to get 4.57088. Notice that we're trying to get as close to 5. And so that's not quite there yet, and so we could continue on, and we could do 10 to the 0.69 maybe. And so if we do 69, we get 4.8977, and of course you can be doing this with whichever decimals you would like. Let's see. To get more exact, you could go ahead and add another digit to whatever it is you're using, so 0.698, again we're just guessing. So 10 to the 0.698. Ooh, that was not what I typed. Gets me 4.9888. Okay, so that's getting there pretty close. If I go ahead and do 0.699, because of course that's a little bit bigger, I'm going to end up with 5.00034. So that's getting pretty close to 5. I can continue on and do 0.69, and instead of a 9, we could do 87. So kind of thinking of this as 90, we could put in 87 instead and see what happens. So let's see, we get 4.99689. We're trying to get as close as we can without going over, so let's go ahead and do 6988, since it's not quite over 5 yet. And that's 4.9980. Getting a little bit closer, so maybe 6989 instead of 88. We get 4.99919. That's pretty close to 5. 0.69897 also works. We could get 4.999999. Actually, lots of 9s. How many? 1, 2, 3, 4, 5, 6, 7. And then a 5. I'd say that's pretty darn close. So we have 0.69897. It does say to 6 decimal places, and so it just turns out that there's actually a 0 after that. So the idea of a logarithm is that it's the opposite operation of an exponent variable. So for instance, whatever this operation is, we could take it to both sides. So if we think of it as a root, because that's kind of what we know, we would have been able to say, oh, 10 equals 0.698970, just by doing this one operation. And so that's actually what logs do. So it's like this, but of course it's not that. It's actually this. So what happens is we are given something in exponential format. And again, as we just did it, it's 10 to the x equals 5. So b would have been our 10, a would have been our 5, and of course x is our exponent. So the idea is that you can use logarithms to use these same points. So notice b is going to go over here to our base. A is actually going to be the thing inside of the logarithm. There are potential parentheses around here. And then the x actually ends up being the exponent, the answer, which is of course what we want. We want to determine what that x is. So if we go back to our previous example and rewrite this, it's actually going to be log base 10, because our base being raised to the x power is all of a sudden the base of our log. And we do call this the base. It's nice that it's got a b in it. I also like to call this one the answer, even though it has nothing to do with that at that point, because it starts with a. Anyway, and of course it's equal to it, so a lot of people think that it's the answer. So 10 is our base. Remember that we know x goes as our result, so that's going to go out here. And then our a, or our answer, is going to go inside of the log. So if we go ahead and evaluate the logarithm with a calculator, you're going to end up being able to type log base 10 of 5 and press equals, and we'll get our result. Your calculator, depending on which one you're using, and I would assume it would be the one on the internet, has a log button all the way on the left, and that is automatically a base 10. So in that case, you can just press that piece, and so on your calculator screen you're going to see log, and then it's going to come up with a parenthesis. You'll type 5 and then end the parenthesis, and you're going to press enter and get 0.698970043, which of course, after guessing and checking, was very close to what we started to get. So that is the idea of our introduction to log. So it turns out that logs are exponents, and inverses are inverse operations of each other. So logs and exponents are inverses. So taking a look at what we have here and what we were doing previously, if we have an inverse, remember that it reflects across the y equals x axis, or that diagonal line. And so as we're looking at this, you can see hopefully that this is our exponent version of this. They both have a base 2, right? They both have our x inside, and then they're equal to the function that we're looking at. So these are going to be inverses of each other based on the fact that we use the base for what's being brought to the power as the base of the log. So all I'm doing in this example here is just showing you that they are going to be inverses visually by graphing each of one of them. So for this first piece here, all I need to do is take 2, bring it to the negative 3 power, and I'm going to get 0.125. 2 to the negative 2 power is 0.25. 2 to the negative 1 is 0.5. 2 to the 0, of course, is 1. 2 to the 1 is 2, 2 to the 2 is 4, and 2 to the 3 is 8. So if we go ahead and graph this piece here, at negative 3 we're going to be almost at 0. At negative 2 it's almost at 0 again. Halfway up at negative 1, 1 is for our 0. Over 1 up 2 is the next one. And over 2 up 4. And then over 3 up 8. So this is what we would call our original function, and then we're going to flip it over this mirror of y equals x. So what we're going to do next is try to do log base 2 of negative 3. What's going to happen is you're going to get an error, and that is because in our first example we have an asymptote at 0. And so if we flip that asymptote across the axis, we actually end up getting an asymptote at the y-axis. And so basically anything past this, which would be negative 3, negative 2, negative 1, is going to get an error because we don't actually get to pass that 0 axis. So on that note, these are all going to be error or impossible until we finally get to the number 1, which is going to be log base 2 of 1, and you're going to end up with 0. So the problem with doing log base 2 is that you can't do it by one single button on your calculator, so you do end up having to go to Math, and then scrolling over to, I believe it's, no, I think you just go down. Again, to get to this calculator, you'd go to Headrush, go to the overview, and then you get the calculator link. Press start, and then the calculator. And so if you go to Math and you scroll down, you are going to get option A. Scroll down. Option A is called log base. And so if you press enter on log base, it's going to bring you to something that has a log with a little box here, a little box here, and so you can kind of fill in what you need. So you can fill in the 2, and you can fill in the 1, press enter, and you get 0. Then if we do the next one, we're doing log, whoops, I'm on the eraser, log base 2 of 4. Log base 2 of 4 gets you 1, and log base 2 of 3 gets you 1.58496. Ultimately, because we are doing inverses, we could just flip each of these values, and so we could have plotted an x value of 0.125 and a y value of negative 3. And that would have worked as well. So, but of course, to prove that it's an inverse, it's hard to use the fact that it's an inverse to prove that. So, all right. So our first point that we actually have is over 1 up 0. So that's this one. Over 2 up 1 is the next one. And over 3 up 1.58. And so you can see that it does start to follow that idea. And of course you could graph more points if you would like. So hopefully you can see that that reflects across the y equals x axis versus just flipping these, because of course we were trying to prove that they were, so we can't use that shortcut. So how do we know that f of x and g of x are inverses from the graph? Remember, they reflect on the y equals x line. In order to see that mirror, of course, I usually end up kind of tilting my screen. You can't see that I'm doing that, but it helps me kind of to visually see that, yes, it is going in that opposite direction, mirror imaged. So then we have a few examples here, and so we're going to change in example 1 this piece from exponent form to logarithm form. So remember that we're kind of using this diagram here with all the colors. So our b, or our base, is going to be the log base. Our exponent is going to be become the answer, and our a, or our answer, is going to become what's inside the parentheses. So what we have here is a log, and we're going to put our base of 6, and then we're going to take our answer and put it inside, and then it's going to equal our exponent. And so if we type this into our calculator, press enter by going to that math key and then scrolling down to option A, you're going to end up having 4 as your outcome. The next one wants to change from log to exponent form, and this is actually the most common that we're going to be doing, because then we can actually solve, because we know how to solve a lot easier with exponents. So how do we do that? 27 as our base needs to be brought to a power, and that power is not going to be 9, that power is going to be 2/3, and then that's going to equal what we have inside, which is 9. Alright, the next one wants you to evaluate by using the relationship between logarithms and exponents. So for instance, instead of typing this into your calculator, you are going to be asked to say, okay, well, we're saying it's 5 as its base, to what power equals 125? So this is kind of the idea of without a calculator. So they're saying without a calculator, how could you do this log? Okay, and this is actually, what they kind of used when they were developing this technique, because they're saying how can we get an operation to undo this having to think of exponents. So then we go ahead and just try, and 5 to the 1 of course is 5, 5 to the 2 is 25, and then 5 to the 3 is actually 125. So then we realize that x is actually 3. Same thing can happen in the next one. So in the next one we're saying our base is 64. Our exponent, of course, is our x. That's the whole idea of exponential functions. And then it's supposed to equal 8. So this is a little different because now we're going down versus up in value. And so hopefully you remember back to exponents, and if they are negative, that means that we're actually kind of decreasing the value. So for instance, I'm going to put 64 to the -1, which is just going to get me a really big decimal, so no thanks. 64 to the -2 makes 2.44, so we're getting higher in value. 64 to the -3. Oh, actually we're getting a lot lower. And so it's not going to be a negative number, and so another number that we could try would be a fraction. Fractions can also reduce things. So for instance, 6 to the half. Oops. Of course, when you type a fraction in an exponent, it gets a little tricky with, well, I mean, not with the calculator you have probably, but you do want to make sure that you have the entire 1 division sign 2 in that little exponent box without getting out of it, because otherwise you're going to end up dividing the number by 2, so that wouldn't work. So it turns out that if you bring it to the half power, it does actually make 8. So 64 to the half power means that an x of a half would work, which of course, if you did it on your calculator, would have resulted as 0.5, but that's the same thing. And then the next one, we have a log, and this is tricky because anytime that they don't have a base written and they just kind of skip over it, that is because it is always assumed to be 10. So, assumed to be 10. So that means we actually have log base 10 of 100,000. And so if we rewrite it, we've actually got 10 to what power makes 100,000. Basically, anytime you have a 10 raised to a power, all you're doing is counting the number of zeros, and then that will be the power. So there are 5 zeros, so x is actually going to be just 5, 10 to the 5th power. Alright, and then the last one, log base 5 of 1/5. And again, you could type that into your calculator, but the whole idea is that you use this without a calculator, and so you kind of go through the channel of 5 to what is going to make 1/5. And hopefully from there you can kind of see that, oh right, that would be a little tiny power of 1, and so to bring it up to look like this 5, we would end up having 5 to the -1. And so x is actually going to equal -1 to get to that. So just a reference back to our fraction powers and our negative powers and scientific notation, in fact. Alright, so hopefully that helps you out with the assignment. You can see in the assignment here, you're going to rewrite things and then using your power of mental math to rewrite and solve.